Good afternoon, everybody. It's really a great pleasure to be here, of course. And I'm really grateful for you to come here to listen to my talk. I will try to continue. Andrei just gave you a brilliant introduction into the past, into all the events which led to the first observation and the first measurements on graphene. And in my talk, I'll try to overview the present state of the affairs in the area, and also probably try to give you a small hint what can we expect from this material in the future. Of course, it's practically impossible to give any comprehensive lecture on this, because even a simple list of all the superlatives of this material would occupy this very slide. It's of course the thinnest, the strongest, the most conductive. For me, what is important are those 3 points there. It's basically those properties which we haven't discovered yet, and it still gives us a lot of pleasure to work with this. So instead, I will concentrate, I'll give you my hit list, and I'll concentrate on 3 key points which I think are the most important ones. First is the fact that this is the first two-dimensional material which is known to us. We often concentrate on its electronic properties or its mechanical properties and forget that its very existence is actually is quite interesting and provide a lot of new hints and a lot of new physics. And then, of course, I'll try to talk a little bit about the unusual electronic properties which we can find in graphene, and speak a little bit on applications, probably something which you're all interested in. So let me start with the fact that graphene is the first ever two-dimensional material which is known to us, and why is it important? And the easiest way to introduce it, the importance of this, is to think about various forms of carbon in terms of dimensionality. Of course, you all know the three-dimensional form, graphite. You use it in everyday life just by writing with a pencil. But then, about 25 years ago, a quasi-zero-dimensional form, so-called buckyballs or cage molecules, those molecules which consist of only a few tenths of carbon atoms, about 1 nanometer in diameter, have been discovered. And then a quasi-one-dimensional form, the carbon nanotubes, is basically 1 nanometer in diameter, but a few millimeters, can be up to a few millimeters long tubes have been obtained. And this is, we generally refer to those as quasi-one-dimensional form. It's quite obvious that the dimensionality too is missing here. And of course, theorists were really ready to fill it up. Many tens of years ago, they introduced a fictitious material. They call it graphene, but it has never been obtained until very recently. Well, the reason why it hasn't been obtained has been mentioned already by Andrei, because generally nature hates low dimensionality. Only the three-dimensional objects are thermodynamically stable, and the low-dimensional objects are not really stable. You can actually see it from this very slide, because I'm cheating a little bit here, because only 2 of those materials really correspond to what is written on the top. Graphite is indeed the three-dimensional one, and graphene is indeed the two-dimensional. But those 2, they actually have some three-dimensional character in it. And you can see it really easily if you think how theorists like to calculate their properties. They would never go straight to graphite or to carbon nanotubes. They will start with something which is much more simpler with graphene, even though it didn't exist until recently. And they would calculate the properties of graphene, and then would consider buckyballs as just wrapped graphene, or carbon nanotubes as just rolled graphene, and graphite as graphene layers which are stuck one upon each other. And you can see immediately from here that also both buckyballs and carbon nanotubes, they have some three-dimensional character in it. I want to say again that this is not coincidental. It's actually just reflects the fact of our life, that the three-dimensional, the low-dimensional materials and objects are not thermodynamically stable. It's every objects around us are three-dimensional. That's probably the largest two-dimensional object which we have pleasure to work with until graphene. Andrei already mentioned that it is the stability of two-dimensional objects and low-dimensional objects is something to do with the thermodynamic stability at high temperature. It means that it is very hard to grow those materials. But very hard to grow doesn't mean they cannot exist. We can actually prepare them if we do this preparation process at low temperature. Of course, if I ask you, is the temperature low? You just came, in this room, you just came from the outside, and it's bloody freezing out there, so it is quite low. And indeed, the room temperature is low enough, and it doesn't prohibit the existence of those two-dimensional crystals. We just need to find a way how to prepare those two-dimensional crystals at room temperature. One of the possible ways is to start with graphite and use its layer structure and try to exfoliate it into individual layers. In fact, you can use the process which is very familiar to all of you. You can simply take a deck of cards and just try to put it on a table, and with a simple slide like this, you would exfoliate it, and then you basically create a few layers, flakes of cards, and then probably even a one-layer flake. That's exactly what we do, and you have those salami slices of graphite, and probably some of those slices are even monolayer thick. The whole process is very similar to simple writing with a pencil. Here I have a special pencil tray, so prepared on a special substrate, so the different thicknesses of graphite can be seen as different colors. The substrate here is this purple one, and then the thick pieces of graphite can be seen as those yellowish bits, and then the thinner it gets, the bluish it becomes, and then those bits which you cannot see are exactly the monolayer. Those are our clients. So, of course, many other people have tried it before. What we done in 2003, 2004 is just we found a new method which allows us to produce large enough crystals, and we can try to study its properties. We managed to attach contacts to those crystals, and we could study its transport properties and optical properties. Well, when I say large enough, you still won't be able to see it on this picture because they are about one micrometer in size. For comparison, the diameter of your hair is about 100 microns, but that's the typical size which we used to deal with the lab and in the lab, and that's we can study its transport properties. Nowadays, of course, we are much better in making those graphene flakes. We can easily make millimeter-sized crystals, and the progress of the recent years in the growing of graphene allows us to have basically meter-sized polycrystalline graphene in our possession. I want to go a little bit away for a few slides, go a little bit away from graphene and try to show slightly broader picture. Of course, many of you know, especially those who have kids or still remember their childhood, they know that pencils, they not only come in gray or in black, they actually come in all different colors. And it means that there is a variety of materials out there which are layered material, and we can in principle exfoliate those materials as well. For example, we can take the blue one and then exfoliate it. We will get two-dimensional crystals of boron nitride. We can take the brown one. It's the niobium diselenide or molybdenum disulfide. Even we can even get monolayers of BiCCO, which is the high TC superconductor. So and all of those materials can be produced at very high quality, and their properties are extremely different from their three-dimensional precursor. And it means that we can get not only graphene, which was the first two-dimensional crystal, but also other two-dimensional crystals as well. There is actually another way how to produce more two-dimensional crystals, and here we would use the fact that graphene, although we usually refer to it as the two-dimensional crystal, it can be also seen as a giant organic molecule, and it means that we can do some chemistry with it. We can, for example, react it with fluorine, and then what we get is the fluorographene or two-dimensional Teflon. If you want, we have one fluorine atom attached to each of the carbon atoms here, or we can do the same trick with hydrogen, and then we get graphene. So the message from this part to take home is that we're not only getting graphene. Graphene is just the one example. We are working now with the totally new class of crystalline materials. It's the two-dimensional atomic crystals. And really, we're only touching the tip of the iceberg now. You can probably call graphene that we studied it a little bit. There are few materials which are lightly touched, like boron nitride, graphene, fluorographene, but there is a whole world out there, for example, niobium diselenide, molybdenum disulfide, quite a few other dihocagonides. And we can produce two-dimensional crystals out of all of them. They are of very high quality, and it's a totally new direction of research, and it's a very exciting time for us. Those materials, they would really cover a huge variety of properties. You basically start with metallic graphene. You can go to insulating boron nitride. Probably we're hoping that they might even show some superconductivity one day, or ferromagnetism. So it is very exciting, exciting area of research. What I wanted to, I just want to show you, to present you with a dream. Those are all existing materials, but we can actually go even a step further. Those cards, you can not only exfoliate it, you can play all the other tricks with those. As you've seen on TV, you can, for example, shuffle it like this. Well, that's actually a good example of turbostratic graphite, and you can, well, that's the procedure which is allowed for the card players in a casino. But of course, physicists, we don't care much about the rules. We can do something extra. For example, I can take two decks of cards, one blue, one red, and try to shuffle two of them together. Well, you can see I don't do it very often. Well, it's what do I get is absolutely useless for a card game, of course. But if you do it with the materials, well, what you get is a completely new material. And what kind of properties will it possess? Well, I don't know, but I'm sure it will be extremely exciting. You can actually go even one step further. You can take a few more decks of cards, and you can, and I mean, actually, nature allows us to have really. I mean, I have only 4 with me, but nature allows us to have many more, and we can do it really one by one. Take one from here, 2 from here, then 3 from here, and so on, and we get a completely new material, really, with the properties which were specifically designed for our needs. Knowing people in the audience, let me ask, especially theorists, not to record the very composition of this material because it doesn't exist yet, but at least those two, they do exist. For example, this one is the bilayer graphene, and you might think, well, what kind of significance would bilayer graphene have? It's only two graphenes just put together. In fact, it has very different properties both from graphene and from graphite. It can be considered as a new material as well. For example, of course, graphene is ultimately thin. Graphite is a layered material, can be cleaved easily. Bilayer graphene, well, you can slide two layers with respect to each other. They're very different in terms of their electronic properties. We have graphite is a semi-metal. Graphene is a zero-gap semiconductor with, a zero overlap semi-metal. That's probably the more correct name for it. With linear dispersion relation, bilayer has parabolic or probably more complicated dispersion relation, and actually a gap can be opened in the electronic spectra. Also, their chemical properties are very different. The other material which I showed you, we managed to produce that one as well. And again, it's the engineering with the of new materials with the layered materials. We have conductive layers of graphene separated by individual boron nitride layers, which is insulator, and then we can attach contacts even individually to those two layers and study the novel properties of those materials. We can actually even tune the coupling between those layers, and it will provide different effects, starting from tunneling here, for example, to pure Coulomb coupling for such materials. So we really have a new way of engineering novel type of materials, which are the two-dimensional crystalline-based heterostructures, and we really can adjust the properties of those materials on demand according to our wish. Let me now briefly turn to unusual electronic properties of graphene. That's something what we are most fascinated with. What's so unusual about this? And I thought a lot how to present it to a wide audience. And let me start from what we usually have in all the materials which are available to us. All the conductive materials which we used to have can be divided into two large classes. Either the charge carriers, they are positively charged like holes, or negatively charged like electrons. Well, those are quasi-particles there, of course. And to give an analogy, I just show you it can be produced an analogy with the countries. If you have a single party system in the country, like in North Korea, you have Communist Party, or in Russia, you have the United Russia. So it pretty much dominates the landscape. And then if you try to connect those two materials, that's how transistors and diodes work. You have some resistance for electrons going here, and that's exactly what happens at the border. If you try to connect those two countries, you would have problem crossing the border. So that's how the diode works. Now, in graphene, we have a complete symmetry between electrons and holes, and it's a chiral symmetry, and it really creates this flow of novel, unusual results. The positively charged and negatively charged particles really are asymmetric in this material, and that's something which you would have in higher energy physics, where you have a symmetry between particles and antiparticles, and that's why sometimes they call what our experiments as quasi-relativistic experiments. If I need to compare this material to the political situation, the best one would be probably United States, where you have a symmetry between Republican and Democrats. Some of the states would be Republican, some of them would be democratic, but still you can go from one state to another without any problem, and that's exactly what happens in graphene. Electrons can be converted from holes to electron without any problem, and that's what gives graphene its unusual properties. As I mentioned, bilayer graphene is a special case altogether. It's quasi-particles. They are massive chiral fermions, and honestly, I'm still puzzled with the country analogy for this material. Please let me know if you do know. So these chiral properties of the quasi-particles, they really ensure this ambipolar field effect behavior, because we have the symmetry between electronic states and the hole states. We can set this material to be either a good electronic matter or good hole matter, and we can go to this fascinating Dirac point where you have neither electrons or holes, and still this material would conduct, and I won't go too much into details of this regime. But what is probably important for applications, that this possibility of electrons going through this material without scattering ensures extremely high mobilities for the devices made of graphene. Mobilities is the measure how far electron can go without scattering, and those numbers are typically 2 orders of magnitude higher than the numbers for silicon at room temperature. Well, again, I won't go too much into details, but it can be related to the famous Klein paradox from the relativistic physics, and this close analogy with the relativistic physics really brings some extra charm to this material. Well, on the practical level, it means that you can make transistors which can work faster. It is thanks to the high mobility, but also to the high Fermi velocity. Basically, people who are interested in high frequency applications, they're trying to get into terahertz regime with graphene transistors. The situation is not as good as bright for the transistors for integrated circuits, because this very linear dispersion relation, or this symmetry between electrons and holes, prohibits us from stopping those particles still, and that's exactly what you need for the successful operation of a transistor. You need to have an on state and an off state, and we have to go a long way to produce working transistors for the integrated circuits. We would have to do single electron transistors. It means very, very small graphene nanostructures. Well, even there are good messages as well, because those nanostructures made of graphene, which are only a few atoms large, they would be very, very stable, and they would sustain extremely high currents. But the bad news is that we simply don't have a technology how to produce those transistors yet. And honestly, it's not a bad news for graphene only, it's the bad news for silicon as well. We simply don't have a technology how to make the next step and go to real nano-size devices for our integrated circuits. In this sense, it doesn't make much sense to talk about if graphene is the next silicon or not. It has very nice properties, but the real problem is the technology. And actually, graphene might offer something even here, because you can think about generally how those nanostructures are created. You start with a flat sheet of graphene or flat sheet of silicon and simply burn away the unwanted parts of this material. In the community, we generally refer to it as paper cutting method. You just carve away those unwanted pieces. But as I mentioned already, graphene can be considered as the giant organic molecule. So in principle, you can use paper painting method. You can run some chemical reaction locally on it. And because this chemistry can be done self-organizing, we can hope for this self-organization to arrange it into certain nanostructures by itself. And hopefully one day we will be using this method to produce our integrated circuits. Well, it won't be complete without mentioning the optical properties of graphene. You might think, what kind of optical properties can it possess? Because it's only one atom thick. We have millions of atoms between me and you, and I can see you easily what kind of, what can one extra atom do? In fact, it can do quite a lot. If you pick up graphene and you can literally do it like this, you would be able to see it, and because it absorbs quite a large fraction of light, namely 2.3%. Well, it means that graphene is extremely optically active, and that's subject of very intensive research at the moment, and people like it to use it for various photonic applications. But also what is fascinating that this number, so what you see here is just a contrast. This is a special sample of graphene. We have graphene stripe here, bilayer graphene here, and then just an empty space here, and you can see the contrast here. This contrast is not given by any material parameters. It's just a combination of very fundamental constants. This 2.3% is exactly pi times alpha. You can do it at home, 3.1415 over 137, you would get 2.3%. Well, it's amazing by itself that a monolayer of carbon atoms absorbs such a large fraction of light, but for electronic engineers, it's a holy grail because it is a very small number for them. They would really kill to have something which absorbs only 2.3% of light and would be as conductive as graphene. This material could be in the heart of any photonic applications like liquid crystal displays or touch screens or solar cells. And here what I have for you is the example of a liquid crystal cell made with the use of graphene, and it works extremely nicely, and it has some advantages in comparison to the usual ones because it is highly stable material. It doesn't degrade with time. Well, it sounds all jolly good. However, I should admit that this size is about 30 microns. And of course, for the TV in your lounge, you probably would like a 30-inch display rather than 30 microns. And that's a big question now. How can we go from the lab to the actual applications? And that's the last topic which I want to cover in my lecture. Before I go there, I still want to be very positive, and I want to show you the applications which are already there, which already do exist with graphene. So what graphene has ever done for us? Well, it helped creating workplaces. There are a number of companies in the world now which trade in graphene. Well, and those, of course, those companies, they all create workplaces. Not many, namely 3, one workplace per company, but in this economic crisis, no job is too small, every penny counts, so it's still good enough. Graphene also provides entertainment. I'm not sure how large is it in Sweden, but this new American sitcom, The Big Bang Theory, is extremely large in US and in UK, and one of the episode was devoted to graphene, where this chap, Sheldon, the string theorist from Caltech, was trying to resolve the graphene problem, and he fails for all the episodes through. And now you should know why, because all the formulas here are not for graphene but for bilayer graphene, and I told you already that those are 2 different materials and you cannot mix them up. It also gives shelter. If you fancy to go and live in Tallahassee, Florida, you can quite as well live on Graphene Lane. Well, houses are not very good yet. For specialists, they're not freestanding yet, but well, it's just the beginning. It's a new street there. They're just building up. So the important message from here is that what I really like, that the first applications of graphene came in some very unexpected area, and I really wanted to keep up like this for the future. And this problem of making large enough graphene sheets, I think it is basically being resolved thanks to the huge progress over the last few years. They can now grow epitaxial graphene on the surface of any metal. Of course, it will be absolutely useless for any applications because it is just a part of the three-dimensional structure, and this metal would short any electric circuit. But you can actually play a trick, and you can transfer it practically to any surface of your choice, and you can create graphene on any substrates you want. I want to mention one more application which probably sounds very minor, but it is already there, and people sell those devices not for research purposes, but as a graphene device. Because it is so thin and transparent and so mechanically strong, it is and also conductive, it is the ideal support for any biomolecules if you want to study those in transmission electron microscope. And it is extremely easy to prepare those devices. You simply pick up this graphene on a substrate, the freestanding graphene, you dip it into a solution with some organic molecules of your choice, and if I can do it, everybody can do it as well. You just dry it up, and here you are. You have, in this case, tobacco mosaic virus on graphene, and you can easily observe it in TEM, and you don't need any staining or any contrast enhancement because it is so thin, and you can also filter out the crystalline structure of graphene, and many companies are now trading in those TM supports. So as I said already, the manufacturing, the scaling up of the manufacturing has been practically resolved. You can now get your 30-inch display with graphene, and it really opens up all the opportunities for graphene applications. And as my conclusion slide, I just want to mention some of them. It should be quite big in photovoltaics, for touchscreen applications, LCD, solar cells, photo detectors, of course, electronics for high-frequency electronics, probably gas sensors, strain gauges, variable capacitors, and there are plenty of more applications which we might see graphene coming out in the next few years. As the last slide, I would like to thank my collaborators. First of all, of course, my teacher, my colleague, and my friend, Andrei Gaim, and all the people in Manchester who've been working with us over the years. Really great bunch of postdocs, very talented postdocs and PhD students, and the fantastic community which we had over the years. I'm really grateful for their support. Thank you so much.